Hello and welcome to another episode of the Omics Casts. Today we're going to talk about the Nanopore update that were given in the London Calling Conference in May 2019. We're going to talk about this by following the plenary session that the CTO Clive Brown and the team gave during the talk, and I'm going to give you my opinion on the different updates and what they mean. So first of all, what is Oxford Nanopore? Why is people excited about nanopore sequencing? The proposition of the company is that it allows people to sequence anything, anyone, anywhere. That they offer simple workflows, libraries that can be made in 5 minutes, no capex, no capital expenditure, and that's something that's portable and scalable. Something that can happen real time, on demand, next to the bedside, very important consideration, and that it is information rich more so than current NGS technologies from people like Illumina or MGI, BGI, in the sense that it can do, for example, modified bases. You can also do direct RNA, which is something biologically more relevant than all that we know about RNA today, which is by a sample prep that turns it into cDNA. Now, how does nanopore sequencing work? Well, compared to Illumina and other technologies that either synthesize DNA by the SBS technology or cleave breakdown DNA or ligate DNA by other technologies that have been used in the past, apart from the sample prep, nanopore sequencing simply reads DNA. It basically processes a molecule through a pore, and while doing so, it looks at the electrical current generated, and it gives you the sequence of the DNA or RNA molecule that has been passed through the pore, right? So there's a motor, there's the pore itself, membrane, and the algorithms that create the final output, and the run conditions, the salt, the fuel, etc. All this contributes to the final outcome. And how many of these pores? Well, it depends on the platform offered by Nanopore. It could be from the low hundreds into the mid hundreds into the mid thousands for the largest of the machines or flow cells that they offer. From lowest to highest, the mean ion is the smallest, and it works either with the flow cells that come from the mean ion or with the smaller flow cells of 126 channels called the Flongles. These allow you to do very cheap experiments. This can give you in the gigabases of data. All this can be plugged directly into a laptop, or if you want to do 5 at a time and have the compute to do the processing, the post-processing of it, you can do it via the grid ion. And then the PromethION is the largest offering currently, either on the 24 or 48x version of it, which can produce data at the scale of the 2 largest other offerings in NGS currently, Illumina and MGI, BGI, and maybe within the same ballpark in terms of long read technology as PacBio, but definitely the PromethION can do the throughput of the big players there, Illumina and MGI, BGI. So the PromethION does on-demand high throughput, and it allows you to itemize your experiments on each of the 48 flow cells that you can put in. If you put in all 88 flow cells and do the maximum called sequencing run, you can achieve over 7 terabase pairs per instrument run. A single flow cell in the ballpark of 180 gigs, median maybe at around 100, depending on the sample. There are samples that are more difficult to sequence, so it's difficult to say if they will always render that amount. What has been doing in the customer hands, many customers that are now in the 4 or 5 terabases when they extrapolate for all 48 flow cells, And there is a customer in China that has broken the record. Here's Clive Brown quoting a tweet that I tweeted when this was publicly released, broken the record of the highest instrument run in the history of NGS sequencing with 7.3 terabases. The other machines out there that do NGS at very high throughput, the Illumina NovaSeq can produce up to 6 terabases. There's never been a reported run of 7.3 or more terabases, even though, it's within the realms of a possibility that it happened. And for the MGI BGI machine, what they call the T7 machine, it currently is spec'd at 6 Ts, at 6 terabases. The fact that it's called T7 means that you can probably generate 7 Ts if you're lucky, but currently it's spec'd at 6 Ts. What is people doing with the PromethION? What science is taking place with it? I have to say, from this conference in May 2019, organized by Oxford Nanopore, to me, one of the biggest highlights is how much of the science and the biology was reported by customers, rather than concentrating on, tedious technical aspects of the technology. The T2T project, telomere to telomere, doing full human assemblies, 100 genomes in 100 days, the tomato resequencing project by Mike Schatz and people in Cold Spring Harbor, the Grandomics, a Chinese company that produced a 7.3 T sequencing run, doing human samples in this case, I think. Moving over to the GridION. The GridION is being upgraded. I think it's mid to late this year. The main upgrade is on the compute side. So it used to have a dual 1080 Ti GPU producing about 22 teraflops and using about 100 watts of power. And now it's gone up to about 5-fold, and it's using even less power at that by using a single NVIDIA Tesla V100 GPU. It seems like Nanopore is banking more and more on NVIDIA products to be able to accelerate the compute that happens on these machines and the assortment of machines they have, the GridION, PromethION, even the Minute, which is a very small machine. And it seems to be a successful strategy or partnership for them to be able to do that. And the base calling, they say, the GridION can do has quite a bit of slack, even if the good news of improving flow cells are deployed to a current GridION box. So this update will probably give quite a lot of room to maneuver for improvements in the flow cells that are loaded in it. The MinION MK1C, it's essentially a Minute, which is this box here. It's like a small computer without a screen, plus a MinION, plus a smartphone. It's got an eSIM, an electronic SIM card inside, so you can transmit data back and forth into and out of the instrument. It's in the ballpark of what a MinION does, but with this level of integration, and can be deployable more easily than the MinION. The Flongle is this small flow cell, which it's now at around 1/10 of what a MinION currently is in terms of throughput. And it's a good development in the sense that because the flow cells for the MinION, the PromethION, have been improving in throughput, sometimes you don't require that much throughput, and you want to do an experiment and pay only, let's say, £100 for it, right? So the Flongle is, I would say, one order of magnitude below of what a MinION currently is, and is allowing a lot of technology out there. Average or median probably at around 1 gig, consistently customers median at half a gig, but quite a lot of room to improve on it. Software, what's been happening with the software? Well, lots of base calling updates. To me, the most substantial is the flip-flop base caller, which is an entirely different way of calling the bases, which sounds like a very promising framework on which to build incremental improvements. The current flip-flop mode is around accuracy of 95%, meaning the number of bases that you get right, 95 out of 100. And it's an evolution of the different technologies that have been used, from HMMs to RNNs as events, the transducer, road transducer, etc. And now with the flip-flop, it's improving the overall quality. And here from Albacore, which is not, it's phased out now, to different versions of Guppy, how the technology has been improving. So if you keep your FAST5 files somewhere in the cloud or in a hard drive, you can continue rebase calling them with the different software. These FAST5 files are about 10 or 20 times bigger than the FASTQ files. So it does take some money or resources to keep them alive somewhere, but considering how much it costs to produce the base calls, why not keep them for a while and then reuse? And so this new flip-flop algorithm is basically better at considering the micro-indels that may occur naturally, micro-indel mistakes that may occur naturally with the technology. And so it takes that into account into the model to do a better job at base calling. And it does better at base calling from both DNA and RNA. It shows here. And they basically have now split into two modes, the fast mode and the accuracy mode. I don't know how I feel about that, because it basically says you can have it fast and low quality, or high accuracy but with lots of compute associated to it. I see how there are different circumstances that people may choose to do one or the other, but I think overall people will still tend to use the most accurate method, and the fast mode will become only important in certain places where you need to deploy it. You need to deploy it in a way that the fast mode is better than the accuracy mode. Training, this is something that will open up, I think, the field a little bit. They released this, again, fish-themed named tool called Taiyaki, which allows you to train even from scratch or from a previous model your own data where you may have done something clever in your sample prep, to be able to generate a model that then you can use for base calling. Main uses probably are going to be modified bases, meaning if you're working on a model organism or some insect or some bacteria or some microbe where there are certain occurrences of modified bases that are particular to you, and there are probably of no interest to people doing human genetics or some other type of animal or plant, then why not have a way for you to train your own data on understood reference data sets or samples, so that you can get a very good accuracy base calling on these modified bases that are particular to you, of particular interest to you and nobody else. And so multiple modifications on one go, essentially, not going beyond the 4 bases and the 5 bases if you count 5MC or 6MA. Doing more than those would then improve people's signal to noise ratio. And so Taiyaki, even though probably not 100% of the people that are interested in nanopore sequencing is something that they're going to investigate and pursue, it's quite nice to see Tim Massingen and the team who have been involved in this releasing this tool and making it available to people. In terms of the technology, the chemistry and the flow cells itself, things that will improve data quality, I have to say I'm seeing Nanopore more and more going into the asymptotic part of their quality, in the sense that the quality they get is quite nice already. And so everything else is, I think, can be considered as easy fixes, and hopefully they'll be able to have a technology that is robust and consistent, comparable as any other NGS technology out there, without any problems. Homopolymers probably the only thing lacking, the only little asterisk or mark that people may complain about Nanopore. Not really that important to a lot of people, but essentially, if you have a series of polyase here, you want to call them well rather than create these micro indels in your calling. And so the new pore, the R10 pore, which essentially pinches the DNA in two places compared to the previous iteration, is much better at homopolymers. It's probably good enough that it may be the last pore that is created by the company just for the sake of quality. Consensus sequence accuracy, they say this R10 pore is a better starting point to get consensus accuracy. That's important, and it's probably, as I say, I'm not that interested in giving the lowdown on accuracy that much, because to me, what's important here is to calibrate the throughput of these offerings compared to Illumina, MGI, BGI, PacBio. The accuracy was a problem a few years ago. I don't think it's a problem anymore. What needed modification from these R10 with respect to the other ones? Unblocking, improving the max scan. Obviously, when you change a big part of a component, you have to tweak and optimize the other parameters. But if you get 26 gigs from a min ion with a R10 and more than 100 gigs on a Prometheus ion with R10s, to me, this means that it's job done and not have to worry about it anymore. Sample prep, important, definitely important consideration. A lot of people want a sample prep that is quick, that doesn't require a lot of equipment, and that it gives you good data at very high throughput. And Nanopore has done well. And probably, I would say, we don't give enough credit to the company for what they've achieved in terms of sample prep. Things like direct RNA is, to me, fantastic. Things like low input, 10 nanograms, but also PCR-free native DNA, rapid in the field for 10 minutes with only 400 nanograms. This is outstanding. And in many ways, they've already achieved more than PacBio has done in a longer history of the company. Automation, the Voltrex V2. This is something that will enable a lot of possibilities. A lot of people, a lot of what one of the Nanopore executives called citizen sequencing, or I call it DIY genomics, being able to do something outside of the realm of academia or the clinical setting, just because it's of interest to you as a citizen, as a private individual. That's very important, and I think it unlocks a lot of creative imagination, creative power of society in general. And the Voltrex, I think, is key to that ability of people to be able to concentrate on what they want to bring to the picture rather than mess around with titrations of sample prep. So I think that's where the Voltrex will have a very nice niche that I think is interesting. UMIs and CCS. So Pacific Biosciences, they themselves are selling one aspect of their technology very heavily, what they call hi-fi or consensus circular sequencing. And they say we can get unique single molecule readouts that are very high quality by simply reading over them over and over, right? And so it's a very fair point from them. It goes, it takes away from your final total high throughput of the technology. It could be tenfold difference, but it's a feature of technology, so why not? Nanopore is not shy about this either. And then either by the use of UMIs or what you're going to see in the next slide, they say, why not? Why not create single molecule, high quality, high Q-score molecules in one way or another? It would help in that. The other aspect is either rolling circle or circular or linear methods that allow the same molecule to be read multiple times. Ideally, you would want this to be PCR-free or native, but for many applications, it does not matter. And so having single molecule consensus equivalent to the PacBio CCS technologies is a plus and an important consideration for a lot of people. And what do you get from this consensus? Well, here this is a plot many of you will recognize by the colors from IGV. And all these dotted grays or blacks are these microindels. If you apply the consensus rate, then it's a lot cleaner. There's one black dot here, which probably, or not, two of them, which probably makes this accuracy not 100%, but you can see how this helps a lot. And the R10, as they say, is a big step forward for them. So how about throughput? How about what's coming from the technology? They are now very similar in where they are with respect to pricing to where Illumina currently is into the three of their main platforms. So the Flongle, which is about a tenth of the mean ion, is around the range of where the Miniseq I would say the Miniseq, where the Miniseq or the iSeq is. And you generate data at around 100 to 100 or $300 per gigabase, right? So low unit cost per experiment, $100, maybe less. High cost per gig, but if you only need to do a certain type of sequencing, the unit price is not that high. Mean ion and grid ion are somewhere in the middle, where the MiSeq or the NextSeq are currently for Illumina and the equivalently named machines for NGI VGI. So they're in the $10-20 per gig to $30-40-$50 per gig, depending on the experiment. Important also that the grid ion gives you the compute next to it, because it turns it a lot more into what a NextSeq is, which is give me the FASTQ files out of this sequencing process, right? So this is the mid-range. And then the PromethION, very encouraging numbers from Nanopore, and also very encouraging pricing. Illumina currently, from their HiSeq-X and their NovaSeq S4 flow cells, are still pricing the human genome at $1,000, or the equivalent that would be $8 or $9 or $10 per gig. And Oxford Nanopore has been very valiant in their pricing here, because they're putting themselves between 2, 3, or even 4 times, 5 times cheaper than the Illumina. And Illumina is currently the #1 contender here. I mean, MGI VGI may have the same pricing, but if you can only use the machines in China, then that's a big restriction, right? So the $1,000 genome is at around $10 per gig. The $2 per gig genome would be a $200 genome. It's when we get between $1 and $3 per gigabase that we're going to reach the next big mark, which is going to be the $100 genome. So we're getting close here, and Oxford Nanopore is probably now the #1 competitor to Illumina that's going to push prices down from Illumina themselves. What about sample prep? What about the per unit pricing of doing a Voltrex V2 experiment? In enough cartridge quantities, 96 here, the unit price of a sample prep would be $200, which is quite reasonable, and per reaction of about $50. I would still want to see these at around 10, and maybe we're only going to reach this if we start using more cheaper methods like the UBIC that they presented. But these are relatively recent numbers, in the ballpark that people will start using them in anger, I'm sure. And here is a big slide showing what's coming next. And I have to say, it's quite a dense slide. There's a lot going on in that slide, as you can see. So this presentation was given in May 2019. And they're saying this is what's for the next 3, 4, 5 months in 2019. My highlights from here are definitely deployment of the R10s, meaning there's going to be a point in the second quarter of this year, second half of this year, where the PromethION R10s are going to be available, and maybe at the end of that year, everybody's going to be doing R10s, right? And so we can leave the R9s behind and concentrate on the R10s and analyzing the signal that comes from them. Software, it's important to keep making it easier for people. Epitomy, for example, end-to-end workflows, that's all nice. More improvements in both sample prep and chemistry, that's definitely important. Voltrex PCR, so being able to PCR your samples on a Voltrex. Voltrex multiplexing, making it cheaper. Whole genome amplification, maybe less interesting, but making a single Voltrex sample price cheaper and more flexible by PCRing it will mean a lot to a lot of people. And then the one more thing moment, for those of you that used to follow Steve Jobs' presentations in last 20 years or so, this conference had the one more thing moment in the plate flongle that I'm never going to call anything else other than that. The plate flongle is essentially a very clever idea based on having a small ASIC, a small disposable ASIC, right? So if the ASIC, the kind of electric bit that goes underneath the biology that happens on top, is this big for a PromethION and this big for a MinION or GridION, they've come up with this little flongle here, which is in comparison to the one pen P, can comfortably lay on the tip of the finger of anybody. It has fewer channels or on top of it nanopores than the other bigger ones, but the key of it is that it's disposable, right? So it's very cheap. You use it once, you dispose of it, and it doesn't have nasty chemicals or anything else. And it's use it and throw it away. So if they can do this little ASICs, what would be a clever way of using it? And I think this is a very clever way of using it. The plate flongle, a 96 well plate format to do small scale experiments in a plate of 96, an 8x12 plate. 8x12 plates, ubiquitous everywhere in molecular biology, and you can do a lot of sample prepping on 8x12 preps from a lot of vendors, very well understood. A lot of technologies already banking on 8x12 formats. And so why not have 96 flow cells in a plate like this, a plate flongle, with enough channels each that you can do low throughput experiments at a very low cost per flow cell or per well in the plate. And so having something in the target of $25 to $50 on a 96 well plate format, I think this is, to me, probably the biggest moment of this update that the company gave in May in 2019. Only available in second quarter of 2020, and it'll come in this nice box, not that much bigger than a MinION, but this will enable a lot of things that relate to diagnosis, things that relate to clinical, because it sets the path for things to come, essentially. A lot of this goes in the order of academia, then clinical environment. And so putting it on an 8x12 96 well plate is a big facilitator to put it on the path of clinical applications. Finally, Clive Brown spent a few minutes talking about DNA writing. I sometimes yawn when people talk to me about DNA writing, and it's something that just comes natural to me. Sometimes I am hugely surprised by it. What they're trying to say is, I think the clever point of it is, let's not synthesize long molecules of DNA. Let's ride on top of existing long DNA molecules that are essentially almost free, and then encode in them every once in a while a base that then we can read back through a nanopore sequencer and read the data back from it. And so Clive Brown and the company go from a kind of a let's make this smaller attitude to DNA writing. And the clever bit to me is, as I say, if nature is so good at putting DNA inside of little boxes that you can unbox and take, why not use that natural ability of so many organisms in this world to use it for something to accelerate the field, DNA writing or storage in DNA that will make a difference. So that was, on top of everything else, to me, the biggest impact is the plate Flongle. And more of the same, a company consistently improving their technologies, pushing the competitors hard to continue delivering innovation and better products and platforms. And I think ONT, who's probably now preparing for the final stages of an IPO, very well positioned in this next generation sequencing market. If you want to learn more about all this, I suggest you have a look at my NGS specs page, where I keep tables of the different specs of different technologies, compare them, make some calculations on where they could go. Follow me on Twitter for more of these, twitter.com/Alberto, and contact me on LinkedIn if you want. I'm happy to answer any questions you may have on this technology. We're having more of those, NGS, Nanopore, other technologies, more of these video casts. So if you click subscribe, you'll get an alert when there is the next one. Until then, goodbye.